Hello again, and we are in chapter 13 where we start looking at maximizing the performance out of the genetic algorithms using the concurrent qualities of the genetic algorithms. So we start by just taking a problem that is very, very simple, which is the one max that we saw in the very first program that was in chapter 3. And this program is the one max start, and it is very simple. It is a length of 10, which is very small. We have a population of 25 generations. We run it to find the solution, which is all ones. So let's run it quickly, and we measure the time that it takes. This program will run, once we start it, it will run very, very quickly. And basically no time at all. We couldn't even measure, it's less than a hundredth of a second. So to make it more interesting, we have another version of this program, and we can compare them quickly. And what we see here is that there is a 3-second delay, and this delay is turning into what we call a busy wait. We have a loop that just keeps looping until that 3 seconds is elapsed and have elapsed, and then during that time it basically keeps the CPU busy because it keeps running in a loop. It doesn't do a sleep, it just keeps looping around. And whenever we do the fitness function, every time we calculate the fitness function, we insert that busy wait in there. So when we run this program, it will take way longer. It will take much longer than the first program. And it will actually be very painful to watch because we have 20 individuals in every generation. Each individual, to evaluate it, takes 3 seconds. So it's about 1 minute per generation, and we have 5 generations. So this is going to run now close to 5 minutes. And one reason that it takes so long is that every individual is evaluated in its turn sequentially. So we evaluated the first, it's 3 seconds, and then we evaluate the second 3 seconds, etc., etc. And this is the point of what we're trying to do here. In the next programs, we are going to try to take those fitness evaluations and parallelize them, have them happen concurrently. So we don't have to wait for each evaluation before we start the new evaluation. That's because they really are not dependent on each other. We have all these individuals, and they can all be evaluated at the same time as far as you're concerned if we have the CPUs available to do them. So we will let this keep going just for the sake of completing it, and we will be back at the end of this run. So finally, this is done, and it comes to symbolize cases where the fitness function is complicated and takes a long time. So we want to have this program run somehow concurrently. And as the book explains, in Python, this is better done using multiprocessing rather than multi-threading, because the Python has some limitation on threads doing things concurrently. So we are going to see a couple of options of making this program concurrent using multiprocessing. So we are going to look at the next program, which takes advantage of the multiprocessing offered by our computer and by the Python language. And if we compare it to the previous program, we can see that the difference is not very large. It's what we do is add the multiprocessing module import, and then we run the same loop as before, but under this with multiprocessing.pool as pool. So that tells the program to run under this pool, and the deep framework lends itself to spread the calculations over the different processors that are available. When we say pool, the computer and the Python running will take advantage of the resources that there are, This computer has 8 cores and 16 logical processors, so it will probably try to use all 16 logical processors. So let's try to run the Python here. So as we will see in a minute, it will go a lot faster than before. The results that we see here, everything that's printed out is identical to what we saw before, but it goes a lot faster. And we see that instead of the 285 seconds, we got only 21.6 seconds, which is maybe 12 to 13 times faster. So this was a very easy way to take advantage of the computing power of the multiple CPUs and cores and logical processors that are available on your computer. So another way to run the program with a parallel execution and take advantage of multiple CPUs is using a library called Scoop rather than the Python built-in multiprocessing. So let's compare this to the original program. So here we, instead of the multiprocessing, we installed a package called Scoop. It's already there in your environment, and we take a module called Futures. And then we register that there is a map module in the Futures or map utility that we tie to our map in the toolbox. This causes a deep to be able to run in parallel over Scoop, and actually deep was designed that way, and that's it. That's the only difference. However, running this program has to be done now from the command line, and I cannot run it directly from the IDE because it has to be run with a certain command. So to run this program, I'm going to open a terminal and run it through the command line in the terminal. So I can do it via for example, via this environment manager and open a terminal in this environment. I have to switch to the directory or the folder where the program is. So I will do cd chapter 13. And now, you see, to the Python command, I add a -m scoop. That means that we are actually using the scoop module, and the scoop module will run for us the program. So when we do that, we can see that it's running on 16 workers. As we saw before, we have 16 logical processors on this computer. And you can also see all kind of warning where futures are being lost and found. There are all kind of communication that is going in the background between, there is a manager thread or a manager process, and it manages all the other processes. But it works out okay at the end, and if you ignore all these warnings and just look at those printouts of the generations here, you will see that we got an identical printout, an identical result, and also in a relatively short time of 26.87 seconds. So this is very similar to running with the pool, but Scoop has an advantage that you can actually run it on several computers that are on the same network. There is a way to configure that. We will not do it in this chapter. What we're going to do is go to the next chapter and see how we can run the same program as a client-server configuration. And then we will see also how to do that using the cloud. So I'll see you in the next chapter.